Hi, I'm Chris Wilson. A topic I frequently get asked about is how to keep online games secure. Today, I'd like to talk about one specific aspect of this, and in my opinion, the most interesting one: game protocol security. When you think about the security of an online game, there are many different things you could mean. Let's go through them quickly. So, first up, we've got the traditional security of the game server. This is making sure that people can't break into the physical server that's housing the online game. And there are ways to do this. You can keep the server firewalled so only you can access it. You can only expose the game service itself so there's no other ports that people can connect to. You can keep the server patched. You can run intrusion detection software. This is all very standard stuff for system administrators, and it's not usually the method that people use to cheat in online games. Secondly, you've got user account security. This is making sure that users are the only ones who can log into their own accounts so that other people can't hack in and get their stuff. And this is usually solved by educating users about unique passwords, adding additional authentication factors, detecting suspicious activity and logins. And while some economic problems come from account theft, they're usually moderately zero sum. And so they're not the type of cheating that we're going to be talking about today, though it is an important area. Next up, we've got detecting client-side modification of the game. Now, ideally, this is solved by making sure that the game runs what's called a server authoritative model, where the server is the one that makes all the important decisions, and the client is merely there to display the state to the user and take their input. Now, of course, some games, like first-person shooters, can't solely rely on this because they need a little bit of information for latency reasons, so that people don't pop as they appear around a corner. And so some information has to be sent to them a bit early. And in these cases, there is some advantage by people modifying their clients to get access to that information. Now, in that case, it's worth running client-side modification detection software, often known as anti-cheat. And in some cases, this could be quite intrusive. There's quite a lot of drama about kernel-level anti-cheat going around where it's deeply embedded inside your operating system in order to be at a lower level than the cheating software that the bad guys are running. This is an important area, but not one that I want to focus on today. So next up, we've got game logic bugs that don't require protocol manipulation. These are ones that can be done with an unmodified game client and no additional tools. For example, there was an RPG a number of years ago where players were able to, without using any tools, just clicking buttons in the user interface, duplicate trillions of gold in its auction house system. Now, of course, because this becomes quite widespread and public very quickly due to no tools being necessary, it's usually possible, once the bug has been fixed, for the developers to roll back this database to the point before it occurred, essentially undoing the economic damage. You can and should try to solve all of the above. But once your team has got these perfect, don't think that your online game is unhackable. In this video, I'll explain that it may still be wide open. I'm going to be talking about logic bugs in games that can be exploited by manipulating the game's client-to-server communication protocol. So I guess we should start with what is a protocol. So let's use an example of going to a concert and handing over your ticket to enter. So a protocol is the communication of information that is expected between two parties. And in this case, the protocol is that you hand over your concert ticket and the ticket scanner person confirms whether you're allowed to enter the venue and where you can sit. So clearly the correct way that people handle this these days is the ticket has a unique code. The guy scans it, it looks the ticket up in a database and makes sure that it's a real ticket before they let you in. And it gives other information like telling when it was booked, how much it cost, where you should be sitting, and so on. But what if their protocol wasn't as well thought out and was missing some steps? Maybe you could hand them a ticket from yesterday's concert and they wouldn't realize the date was wrong and they'd let you in anyway. Maybe you could hand them your friend's ticket, the one they just used, and they'd let you in even though that ticket has already been consumed. Maybe you could alter your ticket to say you were actually sitting in VIP seats and they wouldn't be able to tell, they'd just tell you where to sit. These deficiencies in the checks are what we call protocol exploits because they are where the modification of data to the server causes behavior that was not intended. So what does this mean in terms of online games? Well, the equivalent of handing over your concert ticket is sending a packet of data to the game server. Let's have a look at what a packet is. So let's say in an online game you want to travel to a specific location. So you'd send some data to the server indicating your desire to do so. The first part of the data you send is the packet ID, which is where you say, I want to travel to that location. You then send the X and Y coordinates of identifying where you want to go, and maybe some additional information like whether you want to walk or run to that location. We're going to be getting a little technical in this talk, and that means having a look at exactly how this is represented in data that is sent to the server. So I've indicated the different widths of the fields here. This is how many bits it takes to represent that particular piece of data. For example, the travel to location indicator is in an 8-bit field, giving you 256 possible types of packets you could send to the server, which is typical. The X and Y coordinates in this case are both 32 bits, allowing a very wide game world. And finally, the additional information, whether the character is walking or running, is represented in 8 bits, though I should note, of course, that walk or run could be done in 1 bit, but we like to keep things as a multiple of whole bytes. Now let's have a look at the actual data that's going to be put into this packet. Now in this talk, I'm going to be using hexadecimal notation. This is where a byte of information is represented by 2 hex digits that contain values from 0 through 9 and A through F, representing 16 possibilities per digit. And so each of the bytes here is 2 of the characters you see on the screen, prefixed by 0x. So in this example game, travel to location is packet ID 4. We've set the X and Y coordinates to 6,000 and 8,000 respectively in hex, and travel type is number 1, which let's just say corresponds to running. And so the packet you transmit to the server is the following bytes: 40060 00080 01. And when the server receives this, it's able to decode it and work out what you meant you wanted to do. So you probably want some examples from real games. Thankfully, you came to the right place. Now, a lot of people assume that I just collect Magic the Gathering cards, but I also have a collection of stories about protocol exploits in online games. I'm going to talk about some exploits today without being too specific about what game they're in, though I'm sure you can work it out for a few of them. Also, everything I'm discussing here has been fixed a long, long time ago. I'm going to be fabricating examples of packets. I have no idea what the actual protocols look like for these games. I'm also going to be fabricating some pseudocode showing how the packet handlers on the server likely looked and how we can fix them. Our first example is a relatively tame one. There was a massively multiplayer game a number of years ago that had a packet that the client sends to the server when the player wants to initiate a sit-down action. And this packet contained the player's ID. And so you can see here we send 14, which is a packet number that I've ascribed to it, followed by the ID of the player. Now, on these slides, I'm going to be using big endian notation for simplicity. Some games don't. They send the least significant byte first, but for readability, we're using this notation. When the packet arrived at the server, it had a handler that looked something like this. Now, I'm using a Rust-like pseudocode here for these examples. This obviously isn't what the actual code looks like. But essentially what this one did is it took the player ID the player sent in, it looks at that player and initiates a sit-down request on it. The problem is they were doing no checks at all to make sure that the player was the actual person who initiated the action. And because of this, you could cause other players to sit down. If you sent a different player ID in there, their character would immediately interrupt what it's doing and sit down just like they pressed the appropriate action in their game client. And so in order to fix this, we need to check to make sure that the player ID corresponding to this connection is the same one that's specified in the packet. Now, you may be wondering, why can people even specify a player ID if it must be the one for their own player? And that's a great question. And so a better solution here is to modify the packet so that it just contains the sit down byte. You basically say to the server, I want to sit down, and it says, I know who you are, let's do that. And you don't have the ability to refer to other players. So many years ago, a popular RTS game had the concept of rally points. That's where you can select, say, your barracks and say, when you finish creating a unit, I would like it to run to this location. And you could choose XY coordinates nearby that the building would send the unit to. And this, of course, is useful for RTS players who want to have their produced troops appear at the front of their base or whatever. The packet for this looks something like this. After specifying the packet ID for set rally point, you then specify the building and the X and Y coordinates that you wanted to set it to. Now, they had no checks to make sure that the building was actually one of your buildings. And because of this, it was possible to set the enemy's rally points to an arbitrary location of your choosing, for example, in front of your defenses. So every time they produce a unit, it runs off to get shot by one of your towers. The handler on the server side looks something along the lines of this pseudocode. Essentially, when a building is passed in, it gets the building, sets the rally point, and doesn't consider that the building might not be on the correct team. And so a correct solution would look something like this. In this case, we check the team of the building to make sure that it's equivalent to the one that actually issued the order. Otherwise, it bails out. So the next example is slightly more complicated. There was an RPG that came out a number of years ago that included the ability to identify items using a magic scroll or tome, and the packet it used for that looked like the following. After specifying identify item, you then include the item ID for the scroll that you're using to identify it and the item that you're identifying. And both of these are necessary pieces of information because you could be using a different scroll, and so that's the one you'd want to be consumed. You do need to specify which one it is. The handler looks something like this. The first thing it did was it used the scroll. It then checked to see if the item was a scroll, identified the target, and if that succeeded, it would then destroy the scroll. Now, there's a hole here. If you specify an item that isn't actually a scroll, it still gets used by the handler. And there are various other items other than scrolls that can be used, for example, potions. And so if you pass in a potions ID instead of a scrolls ID, it will successfully consume that, but it doesn't get up to the part of the code that destroys the potion because no item was identified. And this meant that players were able to take a really powerful potion and to use it over and over without it going away. So a way to fix this is to make sure that you always destroy the item if you're using it, and that means moving the use item command to be inside the check right next to destroy item. In another online RPG from around the same time period, they had a trade system that supported the idea of putting stacked items in trade. For example, if you had 5 emeralds and you wanted to put them in trade, you can put all 5 in together. And this meant that the offer item for trade packet had to include a quantity value of how many items from that stack you wanted to move in. And so this is what the packet could have looked like. It specified an item ID and a quantity, the number of units. So while this makes perfect sense for items that can be stacked, the same packet was also used for items that can't be, such as your equipment, and in this case it would always send a quantity of 1. So for example, if I was to put my sword in trade, it would say that Chris has put 1 copy of his sword in trade, which I guess makes sense because I only had 1 copy of that item in the first place. But players worked out that they were able to manipulate the protocol to put 0 copies of their item in trade. And this created a 0-size stack in the trade screen that the other person would get if they accepted the trade. The problem was, because equipment doesn't show a stack size, a sword is just 1 sword, it didn't show that it was a stack of 0 of the sword. It just looked like the sword, but players received 0 when they completed the trade. And so this was essentially a trade hack. People were able to basically lie about the item that the other person would get and scam them to get something in return. The packet handler on the server would have looked something like this. It did some checks to make sure that the quantity wasn't larger than the stack size. It did check some invalid values, but it wasn't thorough enough. And so a fix like this, where it bails out if the quantity you're specifying is 0 for an item, would have prevented this problem. A better solution would be to have a different packet for items that have no quantity, so that quantity isn't even specified. In this case, you just say, I want to put my sword in trade, and have no ability to specify a quantity. And then the server, after doing thorough ownership checks to make sure that you actually have the sword, would then put it in the trade screen. While developing online games, developers often include cheating or internal testing tools in their game clients, so they're able to skip around the world and do things they can't normally do to be able to test the game more efficiently. And one way they can do this is by adding extra fields to packets with that functionality, though it's normal to remove these before you actually publish the game. In this particular MMORPG, the accept quest packet had an unknown field at the end of it. And so if you want to accept, say, quest B7, you specify that, but you also have to include these extra 4 bytes of zeros for no reason. When players looked into this, they didn't find any case where the game client actually sent any value other than zeros, but they decided to fiddle with it. And so they tried setting the final value to a 1. And what they found here was that the quest was accepted regardless of any other conditions. It could be a quest they've already completed, it could be a quest that wasn't even offered to them, and that enabled them to redo quests over and over. Due to this cheating functionality that used to be there and was half stripped out, the packet handler in the server would have looked something like this. Ideally, it would check to make sure the quest status was not started, or whatever the valid status is for you to be able to start a quest. But in this case, it was a check where it also passed if this unknown value is specified as 1. Now, clearly the correct solution here is to remove that data from the packet, remove that data from the handler, and to have no mention of it left in the game. If it's not needed for testing anymore, then it shouldn't be part of the released version of the game. The next exploit is quite an interesting one. In this other online RPG, there was the concept of dismantling items. This is where when you find an item, you can break it down into raw materials instead of selling it to the vendor or whatever, and then I assume that you can use these to craft other items in the game. Now, the packet for that would have looked something like this. You specify the item to dismantle, and that's sensible, right? You do obviously have to say which item you're referring to. Now, their packet handler on the server appeared to do quite a lot of checks. It checked to make sure that if the item had an owner, that the owner was the player doing the dismantle. It checked to make sure that the item wasn't on the ground. It checked to make sure that the item wasn't equipped. It checked a bunch of stuff. And because of this, it wasn't possible to dismantle most of the arbitrary items in the game that you encountered. But they had a small hole, and that was to do with quests. You could go to a quest giver and you could ask to view information about a quest, and it would explain to you what the quest entails, and it would also show you the item you'd receive if you completed the quest. But the way the game worked was when it showed you the item, it did it by making that item, putting it in the quest giver's inventory, and then sending it to you so you can see it as a displayable item. But that gave you its ID, and players worked out that if they dismantle that item that the vendor has, they're able to get the components from it. And then they can close the window, reopen it again, and say, hey, show me that quest one more time, dismantle that item, and repeat, essentially generating infinite materials as a result of merely viewing a quest. And so that's a hole in this functionality here. They didn't include a thing that checks to see if the item is in a vendor, and it just basically wasn't as tight as it should be. And so a better solution might be something like this. In this case, we check to make sure the item is in your main inventory, restricting you to only being able to dismantle items that you physically have in your main inventory. Now, if we're really thinking about it, a lot of the problem here stems from the fact that they're specifying a global ID for an item. They're able to refer to any item in the game, and that the handler has to basically rule out all of the ones that we don't want to consider. So, a cleaner way to do it may be the following. I've changed the dismantle item packet so that instead of including an item ID, it includes an index into your main inventory. So, what I'm talking about here is it puts all the items in your main inventory in a sequence, numbered like 1, 2, 3, and so on, and we're referring to the third item here as the one we want to dismantle. And that means there is no way to refer to items that are not in your main inventory. If you want to refer to an item on the ground or in the shop or on another player, you literally can't, because all you can do is specify numbers up to the number of items in your main inventory. And then as long as your packet handler makes sure that you can't refer to items outside of there, then it's safe. And generally speaking, this is a good way of doing packet handlers for online games. If it's possible to refer to something, it's nice to reduce the scopes and no invalid items may be referred to. So the last exploit I want to talk about is my favorite one, and that's because so many things went wrong at the same time. So this one took place in a massively multiplayer game that came out a number of years ago. And this game had a beautiful world with vast soaring cliffs and beaches and so on. And one of the consequences of vast soaring cliffs is that you can fall off. Now, the game had a problem, and the problem was that they decided they wanted to have a 2D representation of the world on the server for efficiency reasons. Now, I totally understand why, right? Like, if you're doing 2D math for combat, everything is a lot faster, it's a lot simpler, you can just fit a lot more players on the server. 2D is really good. But how are you handling fall damage when you only have a 2D representation of the world? And the way they handled this was that when a player falls off a cliff and hits the ground, the client the player is running kind of reports itself to the server and says, hey, I fell. I fell this distance and I want to take some fall damage. Now, of course, this isn't great because a person manipulating the protocol could just fail to send the packet, right? Like they can modify the client so that it can fall off cliffs and then never sends its own fall damage packet, causing it to never take fall damage. And that's certainly an exploit, right? Now people can run around and not take fall damage. It also lets a player modify the fall damage that they took to maybe a lower value, which is potentially plausible if they're worried about being detected just completely never taking fall damage. Unfortunately, that was only the tip of the iceberg with this packet, so you'll notice that it contains a player ID, and what we learned earlier in this video was don't include player IDs when the only valid one is your own player. So of course the hackers decided to see what would happen if they changed the player ID to someone else, and sure enough, the fall damage they reported was then inflicted on that other player. So now they have an arbitrary damage packet they can send that just instantly kills other players. And when they were testing this, they realized that it worked on GMs. The admins who were in the game to fix problems when people got stuck or whatever, you could just arbitrarily kill them with fall damage. In fact, you could spam the entire range of player IDs because they were sequential and kill everyone on the server apart from yourself if you wanted to. Needless to say, this had to get fixed, and it wasn't pretty because they didn't have the 3D information on the server. It was very hard to just make a small tweak to the handler. So the way the packet handler worked on the server was probably something like this. They specify the player ID and the fall distance, it calculates the fall damage from that, deals it to the player. And as we've discussed, it's very important to restrict the player ID to only be the one associated with this connection so you can't report the fall damage for other players. Now, I was going to do a slide showing how we can remove that from the packet, but to be completely honest, the whole concept of doing it like this is completely wrong. So every exploit we've talked about today occurred in a game where the designers of that game had correctly chosen to use a server authoritative model, even if they screwed it up in the implementation. And every single one of those exploits was probably not introduced by a back-end programmer of that game in charge of security. They were all very likely introduced by gameplay programmers who were just implementing features in the game and not fully thinking through what they're doing. So if you're running an online game and want to keep it secure, what can you do about this? Well, the first step is education. Honestly, show this video to your junior gameplay programmers. It may open their eyes about some of the things that they need to do in terms of server validation of these checks. Do not rely on client-only validation. If you have something checked on the client so that it can't send invalid values, that's just going to get turned off by the hackers. So protocol encryption seems like a good idea, right? I mean, after all, if the protocol is encrypted, how are people going to modify it in transit? But unfortunately, it doesn't really help in this case. Because the game is running on the user's computer, they can pull out the private keys and they can decrypt the protocol. And in many cases, people were using man-in-the-middle proxies where they feed it the private keys from the game client to avoid making modifications to the game client that could potentially be detected. Also, client-side hack detection isn't necessarily very useful here. While it's great for detecting bots and other persistent cheat programs, it doesn't necessarily detect small modifications to the protocol done in very, very subtle ways by attackers. Interestingly, what actually does help is using online game streaming services. If someone's playing a game with something like GeForce Now, then they get no exposure to the actual game client's memory or its protocol. They have no way to actually manipulate what it's sending because they're basically interacting with a streamed copy of the game. Of course, that's not practical as the only way to release your game, but it is an interesting consequence of those services. So to avoid these kind of problems, you basically need to sanitize your packet handlers as much as possible. Consider every code path regarding hostile packets. Basically red team them, and for every parameter that you've got, you have to pretend that someone's manipulating it and see what would happen if they tried different permutations of that. You should cull any unnecessary or debug fields from your packets, just get them out of there. You should look at every ID that you're passing in and reduce the scope so it can only refer to items or other entities that you want someone to be able to refer to in the context of that packet. Also, you should note that if you have shared validation code where your client and server both do the same set of checks on some data, that may expose flaws to the attacker. Once they know that it's shared code, they're able to examine the version on the client that they've disassembled and get a good insight into how the server works. The unfortunate reality is that if you're working on a game with an online economy or competitive aspects, then it's incredibly critical to get all of these things perfect. There are a lot of very smart people who will go through your game with a fine-tooth comb and find these issues to abuse. This kind of thing can completely sink the launch of a new game, as it wrecks the fun for all the players who aren't cheating. And it's a real shame to see the work of hundreds of talented developers go to waste because no one wants to play the game due to a few small oversights in a packet handler somewhere. Developers of these games also need to be prepared to deal with problems that occur after launch. You need to have good logging tools. You need to have databases that can be able to be rolled back. It's important to be able to track where the wealth of the economy comes from, to be able to replay what players were doing in game. There's a whole bunch of stuff there, and I'd be happy to do more videos on that in the future. In addition, this is only the tip of the iceberg with regard to this game exploitation stuff. There's a bunch of other stuff related to timing exploits, lagging servers, save consistency, and so on. If you'd be interested in that in a future video, let me know, and I'd be happy to make that too. In the meantime, thanks very much for watching. I know it was a complicated technical subject this time, but I enjoyed it. Thanks very much. Remember to like the video and subscribe, and I'll see you next time.